everyone. This is a problem solving tutorial, and today we will be focusing on simple harmonic motion. The objective really is to start with a physical problem, translate that into a mathematical description, then solve and predict going back to the physical problem. We start with a simple spring here with mass m and constant k. At time t0, so we give it a kick and it starts oscillating. And let's assume that at time t0 it's found at some distance y0, and my positive y here is upwards, and the velocity at that position or at that time is 0. And at any other time we can describe we want to describe the motion with the position of the mass. So the first thing we want to do is translate this real problem into mathematics. What we start with is a force diagram or a free body diagram. So this is the mass that we have, and we put all the forces that act upon it. The forces that act are the gravity force and the spring force. We know from Newton's second law that we are F equals ma, and that a is the acceleration. And the motion is 1d here, so the acceleration is only in the y direction. So ma equals the sum of the forces that are acting on the object, and that is the spring force and the gravity force. Now, you've learned this in classical mechanics already, but let's assume that this is a completely new physics that you're encountering. So that's not a big deal. So you go to books and you look at what is describing that spring, and now you will see that it's a Hooke's law. And Hooke's law will give you the force on the spring. And the same thing with the gravity law, and then we know that the gravity law can be described as follows: with the minus mg in the to the force would be mg in the minus y direction. The problem that we have has an initial conditions, and that is that at y0 we are found at some position y0. So at y t equals 0 equal to y0, and y dot, which is the velocity at time t equals 0, or at that position, same thing, would also be 0. So these are the initial conditions of the physical problem. So now, after we made this diagram and we know all the forces that are acting upon the object, we can type down the equation of motion. So we have A equals Fs plus Fg divided by m. So A is the acceleration in the y direction, so it's y double dot, equals 1 over m, and then we have the spring force minus the gravity force. It's a 1D motion, so I don't need to give the notation, the vector notation. So I can write y double dot equals 1 over m times ky0 minus ky of t minus mg. The acceleration is 0 at y equals 0, is the equilibrium point. So we find that y double dot would be 0 at y equals 0. That is 1 over m times ky0 minus mg, and that gives us that ky0 has to be equal to mg. So when the object is at equilibrium, the forces are cancelling each other, and there is no acceleration on the object, on the mass. Okay, Now we can rewrite the differential equation y w dot plus k over m times y equals to 0, and this is something you're familiar with now. We can change k over m by omega to the power 2. So we can write y w dot plus omega squared y equals 0. And this is a simple harmonic oscillator, and you know the solution for this equation. So this is the differential equation, this is the equation of motion. It happened that we know the solution. If you don't know the solution, then it's time to solve the equations. After we solve the equations, we make use of the initial conditions, and then we find the actual solution for the physical problem that is given. Alright, so we solve the equations. This is our equation. We have the initial conditions, y at time equals 0 equals y0, that is given. And the velocity also at that time is also 0. If we find a solution which has the right number of arbitrary constants, that would be the only solution. So that would be the one and only solution for the system. And this one can show using the uniqueness theorem. So the solution of this differential equation is given by the following. A times cosine A is the amplitude, cosine omega t, plus phi. So phi is the phase, and A is the amplitude. If you take the derivative, then you get a minus omega outside and a sign here. Now if you substitute t equals 0, from the initial conditions we know that y dot equals 0, so this is 0 equals, and this whole thing with omega t, and t is 0 here, and this gives us phi. So we found out that phi, the phase, has to be equal to 0. And we also make use of the initial condition that y at t equals 0 equals y0, and finally we get into the final result, that is y at any time t equals y0 cosine omega t, with this omega being the square root of k over m, and that would give us a period t which is 2 pi over omega. So now we can describe the this physical system at any moment in time, and we know the period. So basically we can predict where it would be at any moment in time. Let's look at another problem. We have a rod here, and that rod is at time t equals 0 is just standing still. You give it an impulse and then it will have an angular velocity. The angular velocity we denote it by big omega 0. We know the length of the rod. And the same thing now. What we do is we go and make a force diagram. We want to translate the problem into a math problem. So in this case we have the gravitational force, so we have gravity acting, but we also have torque here, and the torque T is equal to the position vector times cross product, the force, and you're free to choose the about which point you want to make the calculation. Normally we take it about a point like point P here, and then R would be 0 there, so we don't need to take care of the torque at that point. And then we'll have only one torque element, which is coming from the gravitational force here. The rod would be oscillating from one side to another. Theta would be changing in time, there would be an acceleration. So the angular acceleration is alpha, is theta double dot. And alpha itself can be written as tau over I. Tau is the torque and I is the moment of inertia. Again, you don't have to remember the moment of inertia for the types of objects. You go to a book and you find out that the moment of inertia is 1/3 ml squared. So now we can write the differential equation with theta double dot equals minus mg, that is the force, times L over 2 sine theta t. That would be the cross product with the length here, and over 2 divided by I, and I is given by the moment of inertia here. So finally we can write the accurate differential equation in this form. Now note that there's the theta double dot here, but there's a sine theta here. If you want to solve this accurately, then we have to keep the theta there, the sine theta there, which means that we won't be able to solve it analytically. We would need to use computer to solve that numerically. But if you want to solve it analytically, then we can make use of small angle approximation if the physical problem is allowing that. So if we are actually looking at small angles here for the movement from one side to another, then you can make use of the small angle approximation. That gives us back to this form of simple harmonic motion. And again, we know the solution for that. It would be in this form: some amplitude times cosine omega t plus phi, and that omega would be the square root of what you have here. So the next step, we solve using the initial conditions that we have. The initial conditions that we have are different than before. So theta dot, what we know is that the velocity, the angular velocity at time t equals 0 equals omega, big omega 0. And theta itself equals 0. So we can write that theta t equals 0 equals 0, and that gives us phi being pi over 2. And theta dot, we take the derivative here, we have a minus omega with a sign here. We know that would be omega, big omega 0 at time t equals 0. So finally we come to this final solution. This would be the theta with this giving omega. Now let's look at a different type of physical problem, something that you probably haven't seen before, because in classical mechanics we did not talk about electricity and magnetism. So this is an example of something that might be completely new to you, and that's fine. Don't be afraid if this is the situation. So the problem is the following. This is the real problem. We have a circuit here, and we want to derive the motion of the current in the circuit. We want to solve and predict, same as before. Now, before, when we had gravity, for example, we know that we had to use the law of gravity because gravity is acting upon the mass, and when we had a spring, we went to Hooke's law, the same thing. Now, you look at electricity and magnetism books, and what you would see that to get what we want to get is the equation of motion, we go to Faraday's law, and that would describe the physics here. So eventually, you would have something like this, and this is the charge. So it's the initial charge is given, divided by c equals minus L di dt. This is a differential equation. So we're going to take it from here now, and you can also find that in the book that I would be the q dt, so we can simply put it as q dot. And that's it. And now you substitute back here, q dot here, you'd have q double dot here. Q double dot here, I'll take it to the other side, will be a plus sign. I'll divide by L. So we will end up with this differential equation. Q double dot plus 1 over LC times Q equals 0. And again, this is a simple harmonic oscillator with omega being square root of 1 over LC. So the solution, you know the solution already for the general solution for the simple harmonic oscillator, it would be in this form, right? It is repeating, it is kind of boring, but it's important to see the whole process and how we move from the physical problem to mathematical problem. And then the initial conditions can be different, and that's what would actually describe the specific situation. So in this case, we would have a cosine omega t plus phi for Q. We want to find the amplitude, we want to find the phase, just as before. We know that the current in the initial conditions was I0, so I at t equals 0 equals to I0. In other words, Q dot at t equals 0 would be I0. So you can take the derivative here, and you know that at t equals 0, that would give you Q0, right, or I0, right? So Q dot at 0 would give you I0. So we are here. And we also know that at t equals 0, the charge is given by Q here. So Q at t equals 0 is equal to Q0. So we have these two now equations with two unknowns, and we find out that tangent phi is given by minus I0 over Q omega 0, and the amplitude is given by Q over cosine phi. So that's it really. The solution for the problem is nothing but this Q here with this A and this phi. All right, that's all.